Jai Hind students, welcome to my YouTube channel, and today we are going to discuss Wheatstone bridge. It's a very accurate device to measure the unknown resistance. It is based on null method. So basically we will be dealing with this particular topic, Wheatstone bridge. Now bridge means, students, in the form of a quadrilateral. So Wheatstone bridge is basically an arrangement comprising of 4 resistors connected in the form of a quadrilateral. I repeat, Wheatstone bridge is in the form of an arrangement comprising of 4 resistances arranged in the form of a quadrilateral. So these are the 4 resistances I am talking about. They are forming the 4 sides of a quadrilateral, right? Suppose this resistance is P, this resistance is Q, this resistance is R, and let us consider this to be X. X, suppose it is the unknown resistance. It is suppose the unknown resistance. So out of these 4 resistances, if the value of P, Q and R are known to us, then the value of the 4th resistance X can be easily determined by null method. So that's the utility of Wheatstone bridge, right? So let's start with the description or the circuit diagram of Wheatstone bridge. So suppose this is point A, let us consider this to be point B, this to be point C, and let us consider this to be point D. A source, this is a source, say of EMF E, is connected between the points A and C along with a key. This is a one-way key. So between the points A and C, a source of EMF capital E and a one-way key, they are connected between points A and C. Between the points B and D, a tapping key, this is suppose a tapping key, and a galvanometer are connected. Tapping key means when you press the key, then the circuit will get closed, current will flow, and if you release it, the key will open. So current will be 0 in that case, right? So that's a tapping key. Galvanometer, students, it's a very sensitive device, and it's a device of low resistance, right? And it is used to detect the current. So when the current will flow in the branch BD, it will show deflection either towards right or towards left, depending on whether the current is flowing from B to D or D to B. And if no current flows through the branch BD, then the galvanometer will show 0 deflection. Right, students? So galvanometer and a tapping key is connected between the terminals B and D. While the resistance R is connected in the points A and B, P is connected between the points A and D, and Q is connected between the points D and C. And the wire whose resistance is to be determined, I am talking about the unknown resistance wire, that is to be connected with the points B and C, right? So let's try to distribute the current in the circuit. Suppose net current is I. This point will act as a junction. Let us consider I1 is the current flowing through this particular point, right? This branch. So if the key is open over here, if the key is open, no current will flow through it. So the same current will flow through the resistance X as well. Same current will flow through the resistance X as well. Now suppose here current I2 flows. So since the key is open, tapping key is open, so no current flows through the branch BD. So the same current I2 will flow through the resistance Q as well. And they will combine together, and again current I will enter the negative terminal of the source, right? As we are aware, there can't be any accumulation of charge at any point in the circuit. Charge will remain conserved, isn't it? So, applying junction over here, I will be equal to I1 plus I2. So, sum of the current entering a junction, it must be exactly equal to the sum of the currents leaving it, right? So, now, suppose on pressing the tapping key, the galvanometer shows 0 deflection. Even on pressing the key, the galvanometer keeps showing 0 deflection. It is in this case that when the galvanometer on pressing the tapping key shows 0 deflection, that the bridge is said to be balanced. So at the balanced condition, the galvanometer shows zero deflection. And if it is showing zero deflection, it clearly suggests that point B and point D are at the same potential. So if the ends of the conductor are maintained at the same potential, then the current would be zero. And in that case, the bridge is said to be balanced. And mathematically, we are going to verify the fact that in the balanced condition, P by Q is equal to R by X. This is what we are going to mathematically verify. This is the balanced condition. So P by Q is equal to R by X. P and Q, they are generally known as the ratio arms, right? And this is valid only when point B is at the same potential as that of point D. Therefore, potential difference is zero, which implies that current flowing through the branch BD is zero, which further implies that galvanometer shows zero deflection. It won't show any sort of deflection. So when these conditions are satisfied, then it is found that P by Q is equal to R by S. And this is the case when the bridge is said to be balanced. So students, once again I repeat, a Wheatstone bridge is an arrangement comprising of four resistances P, Q, R and X connected in the form of a quadrilateral as shown in the figure. Right? Galvanometer and tapping key are placed between the points B and D. On pressing the tapping key, if the galvanometer shows zero deflection, then it is found that P by Q is equal to R by X. It is in this condition, it is in this state of the bridge that the bridge is said to be balanced. So what we are going to prove is, when these are the conditions which are valid, then we'll prove that P by Q is equal to R by X. So let's verify this fact. So we'll discuss it by two methods. Let's consider method 1. Now since no current is flowing through it, therefore these two are connected in series, therefore same current must be flowing through each of them. Similarly, no current is flowing through this branch, so these two will be connected in series, and in series the current flowing across resistance P and Q must be same, each being equal to I2, right? So this point is a higher potential, right? And this point is a lower potential. So current will be flowing along this line, A to B and A to B. Then from B it will be from B to C, and here it will be from D to C. So potential difference between the points A and B, it will be equal to VA minus VB. Current is flowing from A to B. Current, I mean conventional current, it always flows from higher potential to lower potential. And as per Ohm's law, potential difference is given by current multiplied by resistance. What is the current? I1. Resistance offered is R. Put this as equation 1. Right, students? Okay. Then let's consider the points between B and C. Potential difference between the points B and C is VB minus VC is equal to I1x. Put this as equation number 2. Similarly, current is flowing from A to B. So the potential difference between the points A and D would be VA minus VD is equal to I2 into P. And the potential difference between the points B and C would be VD minus VC is equal to I2 into Q. Right, students? So, when VB is equal to VD, then the bridge is said to be balanced. Then the current flowing through the branch in which the collector is connected would become 0. Right? So let's apply this condition in these 4 equations. So what we do is VB equals to VD. Now look, VB is equal to VD. These two are equal. These two are equal. So from equation 1 and 3, their left hand side are equal. So therefore we can equate their right hand side, isn't it? So from 1 and 3, since VB equals to VD, so left hand side are equal. Therefore I1R would be equal to I2. Put this as equation 5. Similarly, consider equation 2 and 4. When VB equals to VD, when VB is equal to VD, then look, these two will become same. Therefore, left hand side of equation 2 and 4 are same. Therefore, the right hand side can be equated. Therefore, I1x would be equal to I2q. Now, dividing these two, we should get the result. So, 5th divided by 6th. What we get is I1r divided by I1x is equal to I2p divided by I2q, which implies that P by Q is equal to R by X. Hence, it is verified. Right, students? So, this is a simple mathematical step by using the concept of potential difference, which is equal to the current flowing through that resistor multiplied by the resistance value. So, using this concept, we can easily prove that when the bridge is in the balanced condition, that is when no current flows through the branch BD across which galvanometer is connected, then P by Q is always equal to R by X. So, this is known as the balanced condition of the Wheatstone bridge. So, Wheatstone bridge, students, it is basically based on null method. So, that is the reason why Wheatstone bridge is much more preferable in giving the accurate value of the resistance of this wire. Right? It can be used to find accurately the resistance, unknown resistance. So, no need to calculate the potential difference, no need to calculate the current. So, therefore, we did not to use voltmeter or ammeter. Therefore, the drawbacks of those devices will not come into play while measuring resistance by using Wheatstone bridge. So, that's the advantage of Wheatstone bridge over other devices. So, if you are aware of these three values, the unknown value x can be easily determined. RQ divided by P. So, that will be the working formula by which the value of x can be easily determined, which is the unknown resistance. So, now students, what we can do is, we can verify this condition, or rather we can obtain this condition by using Kirchhoff's laws as well. We will make use of junction rule as well as loop rule so as to obtain this condition. So, let us try alternative method so as to find out the result. So, we are going to prove the same result but by using Kirchhoff's laws, right? So, this is the alternative method. By using Kirchhoff's laws. So, let us first distribute the current. Look, current I is entering this junction if current I1 flows through this branch. Therefore, the remaining current would be I minus I1. Look, at any point on the junction, the sum of the current entering the junction must be exactly equal to the sum of the current leaving it, isn't it? I current is entering and I1 and I minus I1 are leaving. So, if you add these two, you should get I only. So, that verifies junction rule. It's based on the law of conservation of charge. Suppose the tapping key is closed. Let us consider the tapping key is closed, right? So, from here also the current can flow. Let us assume the current flows from B to B. Suppose it is I2. So, current I2 is flowing along branch BD. So, what is the current left from I1? I2 current flows through branch BD. So, the current left that will be flowing through BC would be I1 minus I2, right? If this is 5 ampere, this is 2 ampere, then 3 ampere will go in the branch BC. Again, apply junction rule. Sum of the current entering the junction is equal to the sum of the current leaving it, right? So, this will be junction. Current entering this junction is I minus I1. Current entering this junction from this branch is I2. So, the current leaving this junction would be I minus I1 plus I2. Correct, students? Now, these are the currents entering. So, if you add these two, the net current should be I. Right? So, let's check it out. This is junction where the currents entering are I1 minus I2, and from this branch the current entering junction C is I minus I1 plus I2. If you add these two, you will get I. It means that your current distribution in the various branches of the circuit is perfectly correct. Right, students? Okay. Suppose this G galvanometer, it offers resistance capital G. Suppose it offers resistance capital G. So we have made use of junction rule. Now let's make use of loop rule. So consider this loop. So consider loop ABDA. We are considering the loop in the clockwise direction. Now in this loop there is no EMF. So applying loop rule, we get 0 is equal to I1R plus I2 into G. G is the resistance of the galvanometer. And loop is measured in the clockwise direction. And here current is in the anti-clockwise direction. So it will be minus I minus I1 into P. Put this as equation number 1. Correct, students? Or you can rearrange this. Anyway, let's consider the other loop. Consider this loop. This one is the first loop, this one is the second loop. So I'm considering this loop, B, C, D, D. Right? Again in the clockwise direction. So as to obtain the other equation. So consider loop B, C, D, D. Again, let's make use of the loop rule. This is the loop I am considering, it's a closed loop. So no EMF is in this loop. So therefore net EMF in the loop is 0. And it is through resistance X, the current flow is in case I1 minus I2 and in the clockwise direction, so it will be assigned positive side. Okay. Here the current is flowing in the anti-clockwise direction, so it will be assigned negative side. Minus I minus I1 plus I2 into Q. Right? And we are considering the measurement of the loop in the clockwise. So here current is flowing in the anti-clockwise. So it will be minus I2 G. Right, friends? Put this as equation number 2. So we have obtained two equations by considering those two loops both in the clockwise direction. And as you are aware, whether the loop is measured in the clockwise or anti-clockwise direction, you will get the same expressions, you will get the same statements, right? So now what to do is, when the galvanometer shows zero deflection, then what is the current flowing through this branch? It will be 0. IBD, which is considered to be I2, it will be equal to 0. We are deriving the condition when the bridge is balanced. And students, the bridge is balanced only when no current flows through the galvanometer. Since no current is flowing through the galvanometer, so I2 will be equal to 0. So substitute this value of I2 as 0 in equation 1. So if I2 becomes 0, this term gets eliminated. So what you get is, from this equation what you get is I1R minus I minus I1 into P is equal to 0. Or I1R is equal to I minus I1 into P. Put this as equation 3. Correct? This we have obtained from first. In the balanced condition, the galvanometer shows zero deflection. So substitute the value of I2 as 0 over here and we'll get this particular expression. Right? Now, from second, again substitute the value of I2 as 0. So this term gets eliminated. I2 0 means this will be 0, this will be 0. So we'll be left with I1x minus I minus I1 into Q, it will be equal to 0. Look, here we will be left with I1x, I2 becomes 0. Here we will be left with I2 is 0. So we will be left with minus I minus I1 into Q. And this term will get eliminated as I2 is 0. So we will be left with this, isn't it? So it can be further modified as I1x is equal to I minus I1 into Q. Put this as equation number 4. Now, just check these two, third and fourth. You can divide these two. The coefficient of I1 in both these equations is same. The coefficient of I1 minus I1 actually. It is same in both the equations, isn't it? So, third divided by fourth. What do you get is I1R divided by I1x is equal to I minus I1 into P divided by I minus I1 into Q. So what is left is R by X is equal to P by Q, which is the balanced condition. So students, it's your wish either to derive this condition by the previous method or by this method using Kirchhoff's rules, both the junction rule as well as the loop rule. So again I repeat, a bridge is said to be balanced only when no current flows through the galvanometer or the galvanometer which is connected between the terminals B and A shows zero deflection. And students always remember, in the balanced condition, P by Q is always equal to R by X, right? So there are some numericals which we will try to solve using this balanced condition. So I hope you have understood the derivation part, right? So now let's solve some simple numericals based on Wheatstone bridge, based on balanced Wheatstone bridge. So let's consider on the first question. Suppose a bridge is given like this. The value of this resistance is 2 ohm, this is 4 ohm, this is 6 ohm, and this is suppose X. And let us consider this to be 3 ohm. And this is given, this is point M and this is point N. And a source is connected like this. Right? Suppose it's of 10 volt. Now in the question, it is given that points M and N are at same potential. If it is given that in the given circuit, points M and N are at the same potential, determine the value of X. Right? So what to do is, first and foremost, checking this circuit, we can easily check that these four are connected in the form of quadrilateral. So in such circuits, first you need to check whether this bridge is balanced or not. It is given in the question. Points M and N are at the same potential. So no current flows through the branch M and N. Since these 2 points are at the same potential, therefore no current flows through this branch. Therefore, this branch, no current is flowing, so it can be taken out. So the circuit gets reduced to this one. Right? Now it is in the case of a balanced bridge. So since M and N are at the same potential, therefore the bridge must be balanced. And in that case, these are the ratio arms, isn't it? In that case, 2 by 4, it would be equal to 6 by X. This is R, this is X, this is P, this is Q. In the balanced condition, P by Q is equal to R by X. That is what I have written over here. Right? So what you get is, X will be equal to 6 into 4 divided by 2. So it will be 12 ohm. Clear students? Very, very simple. So you can find out the net resistance also in the circuit and the current flowing through each branch, that can also be found. So this was just a simple application based on Wheatstone bridge. There are some other questions as well which we can try. Right? There are some other very good questions. So let's try the second one. Let us consider a circuit to be given in this particular manner. This is the circuit given. This is point A, this is point B, and these are the resistors which are given like this. And let us consider this to be point X, this to be point Y, and this to be point Z. Let's consider the value of this resistor to be 1 ohm, this to be 3 ohm, right? And this to be 2 ohm, and this is to be determined, and this to be 10 ohm. Clear students? This is the circuit given, this is the circuit given, and you are supposed to find out the value of the unknown resistance. As stated earlier, first check for the balanced condition of Wheatstone bridge or not. First check whether the circuit can be converted in that form or not. Right? So what to do is, a source is connected in A and B. right? So it's understood a potential difference is maintained between the points A and B. So what we'll do is, we'll try to stretch it like this. We'll try to stretch this circuit. So stretching, how it becomes is, it will be like this. Look, this will be the diagram. This is point Z, this is point Y. This will remain fixed, isn't it? This is 3 ohm and this is the resistance whose value is to be determined. Now it is being stretched. So this one will be point B, right? And this is open, the circuit is opened like this. It has to be opened like this. So the modified diagram would be somewhat like this. When you open the circuit, it will be taking form of this particular shape. This will be 2 ohm and YZ. This will be fixed, this is 10 ohm. And point A will lie somewhere over here. It's clear, students? Just try to open up the circuit and the circuit gets modified in this particular manner, right? Like this. So point B comes over here and then point A will take its place over here. Now it becomes very simple. Now check whether it is balanced or not. And it is given, in the quotient it is given that no current flows through the branch YZ. It is given, no current is flowing through the branch YZ. It is given. So I repeat the quotient, students. This circuit is given and it is also stated in the quotient that the current flowing through the branch YZ is 0. You are supposed to determine the value of this unknown resistance. So first convert it into a conventional bridge, isn't it? Thereafter check for its balanced condition. Since no current flows through this branch, therefore the bridge must be balanced. This is P, this is Q, this is R, this is X. These are the ratio arms. They are proportional, isn't it? So since the bridge is given to be balanced, therefore 1 by 3 would be equal to 2 by, suppose its value is X. So X would be equal to 6 ohm. This will be the answer. I hope you have understood the concept, how to make use of the balanced condition of Wheatstone bridge. So these are, students, some very, very interesting questions. In the next lecture also we will try to discuss some more numericals based on Wheatstone bridge, right? So I hope, students, you have watched this video till the end and you are totally convinced about this particular topic. And there is an experiment based on post office box which is based on this Wheatstone bridge only. So now you will be in a position to perform that particular experiment, right? So do take very good care of yourself and we'll continue in the next lecture then, right? Till then, bye-bye and do take very good care. Thank you.